Hello everyone. Today I am going to explain about complex functions differentiation, fourth unit from Laplace transforms, numerical methods and a complex variables subject. Going to the introduction about the complex number first. So the complex number z is a number of the form x plus iy. So here x is a real part and y is a imaginary part. So that's why we can write z is equal to x plus iy. X is equal to real part of z and y is equal to imaginary part of z. And x and y are real here and I value is I is equal to root minus 1 because of I square value is minus 1. If x is equal to 0, z is equal to iy is purely imaginary number. Going to the conjugate of complex number to the z is equal to x plus iy is denoted by z bar or z star. Is found by replacing I by minus I in z. So that's why we can z bar or z star equal to x minus iy is a conjugate of a complex number. Two complex numbers are equal if and only if their real part and imaginary part both are equal, then we can say that two complex numbers are equal. So a complex number polar form right by using z is equal to x plus iy. We are substituting x is equal to r cos theta and y is equal to r sin theta. Then we can get z is equal to r common cos theta plus I sin theta. So here cos theta plus I sin theta is equal to e power I theta. So that's why we can write z is equal to r e power I theta. So here we can find the r value by using xy quadrants, that is r is equal to under root of x square plus y square, means that x value is r cos theta, y is equal to r sin theta. If you substitute it, we get the r square is equal to x square plus y square, r is equal to under root of x square plus y square, and here theta value is tan inverse of y by x because of arc z is equal to arc tan of y by x, and the limits are minus pi to pi. So that's why theta is equal to tan inverse of y by x in the polar form. So polar form always we know that right by using r and theta, and we know x is equal to r cos theta and y is equal to r sin theta. That values is substitute in the complex number, we get a polar form of the complex number. Then going to next, functions of complex variables. So functions of complex variables, already complex variable z is equal to x plus iy. We can write the function for z, we get the f of z. F of z is equal to w, that w equal to u plus iv, that is also one of the complex variable. So that's why we can discuss the complex functions in the domain D. That is, suppose D is a set of complex numbers. A rule f is defined on D which assigns to every z in D. A complex number w is called a function of f or mapping f on D, and we write w equal to f of z. So we write w equal to f of z, that is equal to u plus iv, where u and v are real, and we know that z is equal to x plus iy, and z depends on x and y. U and v also depends on xy, so that's why we can write u is equal to u of x comma y and v is equal to v of x comma y. So w equal to f of z is equal to u of x comma y plus iv of x comma y, where u and v are real and imaginary parts of w equal to f of z. That is the complex function to the variables x and y and u and v. So going to small example to separate the real and imaginary parts from the given f of z, that is, if w equal to f of z, that is equal to z square plus z, find its real and imaginary parts. Also find f of z at 1 plus I. So first we have to separate the real and imaginary parts from f of z, that is, w equal to f of z is equal to z square plus z. Z value is x plus iy, substitute it, x plus iy whole square plus x plus iy. So we can expand by using a plus b whole square, that is x square plus iy whole square. So iy whole square means I square y square. I square value is minus 1. So that x square minus y square plus 2ab term is 2ixy plus x plus iy, that is x square minus y square plus x is a real part, means we can separate the real and imaginary parts. X square minus y square plus x plus I common we have 2xy plus y. So that's why here real part is x square minus y square plus x and imaginary part v is equal to 2xy plus y. We can write here u and v values, and finally you can find f of z at 1 plus I. So here x plus iy value is 1 plus I. We can substitute it 1 plus I whole square plus 1 plus I, that is equal to 1 plus I square minus 1 plus 2I plus 1 plus I. So 1 cancel, we get here 1 plus 2I plus I 3I. 1 plus 3I is the value for f of z at 1 plus I. We can separate the real and imaginary parts by using the z value x plus iy and substitute in the given function. We can separate as a real and imaginary parts. Next definition is limit of f of z. This is the basic definition for continuity, differentiability and analytic function for the next definition. So that's why here the limit of f of z is the number L is called the limit of the function f of z as z tends to z0, then f of z approaches to L. That is limit z tends to z0 f of z is equal to L is the symbolic form of the limit function. If for epsilon greater than 0 there exists delta greater than 0 such that modulus of f of z minus L is less than epsilon, whenever 0 less than mod z minus z naught less than delta. If the f of z and z minus z naught satisfy these two conditions, then only this limit function is exists in the given neighborhood in the z plane and w plane. So here what is epsilon and delta? Epsilon and delta are the small real numbers and we can call as epsilon disk and delta disk. Disk means it is in the shape of the circle. So that's why in the epsilon disk and delta disk both are taken, one is z plane, one is in w plane. Then in the z plane we can take the function z, then we can take the mapping in the w plane, that is f of z through z tends to z0, then limit z tends to z0 f of z is equal to L by using the z plane and w plane with the help of epsilon disk and delta disk. Epsilon and delta are the small real numbers. So if these two conditions are satisfied, that is modulus of f of z minus L less than epsilon and 0 less than mod z minus z naught less than delta, then this limit function is exist for f of z. So next definition is continuity. So here continuity, simply we can say that limit z tends to z0 f of z is equal to f of z0. If this condition is satisfied in the given domain of the neighborhood of z0, then we can say that f of z is continuous. So before that it should satisfy more two conditions, that are a function f of z is said to be continuous at a point z is equal to z0 in its domain if the following three conditions are satisfied, that is f of z0 exists, means that if you substitute z0 value in f of z, that must be finite. Then limit z tends to z0 f of z exists, means that right hand side limit and left hand side limit both are finite, then a limit function is exist. Final condition is, that is limit z tends to z0 f of z is equal to f of z0. This is the very important point for continuity of f of z0 at z is equal to z0. Next definition is differentiability. F of z is said to be differentiable at the point z is equal to z0 if the derivative f dash of z exists at every point in its domain, it is given by f dash of z is equal to limit z tends to z naught f of z minus f of z naught by z minus z naught exists. Means that in the given domain at z is equal to z naught, this differentiable function is exist with the limit, then only the function is differentiable at z is equal to z naught. For a function to be differentiable at any point z is equal to z naught in its domain, it must be continuous at that particular point, but vice versa is not always true. Means every differentiable function is continuous, but every continuous function need not be differentiable. So very important definition is analytic function. Analytic function means a simple, we can say that is f dash of z exists at z is equal to z naught, then f of z is analytic. We can say in the domain, then we can write as a function f of z is said to be analytic in a domain D if f of z is defined and differentiable at every point of D. F of z is said to be analytic at a point z is equal to z naught if f of z is differentiable in some neighborhood of z naught. Another term for the analytic in D is holomorphic in D. So analytic function or holomorphic function, we can say any name to the analytic function. So in the domain, if you say it is analytic, so f of z must be differentiable at each and every point in that domain. We can say that the domain is analytic. Otherwise, we can say f of z is analytic at z is equal to z naught, means that f dash of z exists at z is equal to z naught. Functions which are analytic or holomorphic in the entire complex plane are said to be entire function. So if you take any plane, in that plane each and every point the f of z is analytic, then that entire plane is complex plane is called entire function. Next one is singular point of analytic function. So if we already discussed, analytic function means f dash of z exists at a particular point. So at which the function is not analytic, means that f dash of z is not exist at any point. That point is called singular point or singularity of the f of z. A point at which the function f of z is not analytic, that is at which f dash of z fails to exist, is called singular point or singularity of the function. Note that to find the singular points, equate the denominator to 0 and solve for z. Means that any given f of z is right in the form of phi of z by psi of z. That is, f of z is equal to, here we have a example, z square by z minus 3 into z plus 4. We can equate denominator to 0. We get z is equal to 3 and z is equal to minus 4. That are the singular points. Next one is Cauchy-Riemann equations, that is called CR equations. So the CR equations are right for using partial differentiation. If u and v satisfies the continuous partial differential equations or the partial differentiation, then we can write the CR equations, that is the necessary and sufficient conditions for the derivatives of the function f of z is equal to u of x comma y plus iv of x comma y to exist for all values of z in domain R are dou u by dou x, dou u by dou y, dou v by dou x, dou v by dou y are continuous functions of x and y. And we have two equations, that is dou u by dou x is equal to dou v by dou y and dou u by dou y is equal to minus dou v by dou x are known as CR equations. So means that if these four partial derivatives are exist, it satisfies, f of z satisfies dou u by dou x is equal to dou v by dou y and dou u by dou y is equal to minus dou v by dou x, then that the two equations are CR equations, and it is also an analytic function. That is, if f of z satisfy that CR equations, then f of z is called analytic function. But every analytic function need not be satisfied CR equations. So going to the example on analytic function, determine whether the function f of z is equal to z bar is analytic or not. That is, let f of z is equal to f of x plus iy equal to, they give z bar, that is x minus iy, that is equal to z bar. Here we can take real and imaginary parts. U of x comma y is equal to x and v of x comma y is equal to minus y. So first order differential equations are existent, continuous. So that's why we can find dou u by dou x is equal to 1 and dou u by dou y equal to 0 because of u is equal to x and we have only x terms, there is no y terms, so that's why derivative is 0. Next, going to dou v by dou x is equal to 0 because of there is no x terms here, the derivative value is 0. Dou v by dou y is equal to minus 1. So in the CR equations, dou u by dou x is equal to dou v by dou y. The first condition is not satisfied from the CR equations. So that's why, that is 1 equal to dou u by dou x, that is not equal to dou v by dou y, that is equal to minus 1. So CR equations are not satisfied. That's why we can write f of z is equal to z bar is analytic nowhere. So are not analytic, simply we can write it. Then next example is determine whether the function f of z is equal to e power z square is analytic or not using the Cauchy Riemann equations. Means by using CR equations we can find the function is analytic or not. So that is, first you have to write f of z equal to e power z square, z is equal to x plus iy whole square. Then we can separate as real and imaginary parts by using expansion of x plus iy whole square, that is e power x square minus y square plus 2ixy. So this is also write as e power a plus b, write as e power a into e power b. So here in the place of a we have x square minus y square, that is e power x square minus y square into e power 2ix. So e power I theta formula is cos theta plus I sin theta. Here in the place of theta we have 2xy. So that's why we can write e power x square minus y square cos 2xy plus I sin 2xy. And we can easily separate the real and imaginary parts here. U is equal to e power x square minus y square into cos of 2xy and v of x comma y, imaginary part, e power x square minus y square into sin of 2xy. So e power x square minus y square is multiplied with both real and imaginary parts of cos 2x plus I sin 2xy. So that's why we can write u and v. After that, go to the partial derivatives. First you have to find dou u by dou x. So you should find by using the formula d by dx of uv, that is uv dash plus vu dash. So that's why we can write here u v dash e power x square minus y square cos u v dash. First we have to write cos 2xy and e power x square minus y square derivative is e power x square minus y square into x square minus y square derivative is 2x. Next, going to plus, but we write a minus because of here e power x square minus y square is as usual you can write it. V dash we have to find, that's why cos derivative is minus sign, that's why here minus e power x square minus y square. Cos 2xy derivative is sin 2xy and 2xy derivative with respect to x is 2. So here the common value is e power x square minus y square, right outside we can get 2x cos 2xy minus 2y sin 2xy. After that you can go to dou u by dou y with respect to y, same you can find it e power x square minus y square into x square minus y square derivative with respect to y is minus 2y cos 2xy minus e power x square minus y square into here cos derivative is minus, so that's why here we can write minus and cos derivative minus sin 2xy into 2xy derivative with respect to y is 2x. So then write 2x here. Here also we can common e power x square minus y square. Minus also we can common minus e power x square minus y square. 2y cos 2xy plus 2x sin 2xy. So next going to v. V differentiation also we can use uv form uv dash plus vu dash, that is first you have to plus no, so then you can write the terms any order. So that's why e power x square minus y square derivative is e power minus x square, e power x square minus y square into 2x sin 2xy plus e power x square minus y square into sin derivative is cos 2xy into with respect to x 2xy derivative is 2y, write it, and e power x square minus y square is common, then write 2x sin 2xy plus 2y sin 2y. Next dou v by dou y. Dou v by dou y is equal to e power x square minus y square of with respect to y, no, so minus 2y sin 2xy plus e power x square minus y square into 2x cos 2y, because of here we can write the derivative for sin is cos 2xy and 2xy derivative with respect to y is 2x. Here common term is e power x square minus y square, 2x cos 2y minus 2y sin 2y. So going to CR equations, dou u by dou x is equal to dou v by dou y. This condition is satisfied or not, we have to check it. So dou v by dou y, e power x square minus y square, 2x cos 2y minus 2y sin 2y. So once we have to check dou u by dou x, as dou u by dou x is e power x square minus y square, 2x cos 2y minus 2y sin 2y. Both are equal, so first condition is satisfied. Next going to dou u by dou y. Dou u by dou y is equal to minus dou v by dou x. So here dou v by dou x is equal to e power x square minus y square, 2x sin 2y plus 2y sin 2y, and dou u by dou y having minus, so that's why we can write dou v by dou x is equal to minus dou u by dou y, or simply dou u by dou y equal to minus, we can substitute e power x square minus y square, 2y cos 2xy plus 2x sin 2xy is equal to dou v by dou x. Then both the CR equations are satisfied. That's why given f of z equal to e power z square is analytic by using CR equations. Next form is polar form of CR equations. So polar form of CR equations write by using the r and theta. So let f of z is equal to f of r e power I theta. Already we discussed polar form of z is equal to r e power I theta, that is equal to u of r comma theta plus I v of r comma theta be a function of continuous partial derivatives. Then f is differentiable at z is equal to r e power I theta if and only if dou u by dou r is equal to 1 by r dou v by dou theta and dou v by dou r is equal to minus 1 by r dou u by dou theta. These are the two equations for polar form of CR equations. So we are using r and theta. Dou u by dou r is equal to, it should satisfy 1 by r dou v by dou theta, and dou v by dou r is equal to minus 1 by r dou u by dou theta is the CR equations of the polar form. One small example, that is if w equal to log z, find dw by dz and determine where w is not analytic. So we can show that it is not analytic and we have to find the differentiation of given w value. Here w equal to log z. So if you find the function is analytic or not, we need to check the CR equations. CR equations means we have to write u and v separately, means we can write the given function as real and imaginary parts. So that's why here the function is in log. So that's why it is not possible to separate with Cartesian form. So that's why we can go through with polar form, separate the real and imaginary parts. After that we can go to the Cartesian form, that is, let us consider z is in exponential form. Z is equal to r e power I theta, that is equal to r cos theta plus I sin theta. So here r is equal to, already we discussed, under root of x square plus y square, theta is equal to tan inverse of y. If you substitute w equal to u plus iv equal to log r e power I theta, it is in the form of log AB. Log AB write as log A plus log B. So that's why we can write log R plus log e power I theta. So that is log R plus I theta log E. Log E value is 1. So that's why log R is log of root x square plus y square. That is also write as log of x square plus y square whole power 1 by 2 plus I theta. Theta value is tan inverse of y by x. So log x whole power log x power a is equal to a log x. Here in the place of a we have 1 by 2. So that's why we can write 1 by 2 log of x square plus y square plus I tan inverse of y by x. Otherwise we can directly go through with the polar form also. We can change into Cartesian form. Any procedure you can follow. If you have to solve with r and theta, then you can satisfy with polar form CR equations. Otherwise you can go through with Cartesian form CR equations. Here we are changing into Cartesian form x and y. So that's why we can check the CR equations in the Cartesian form. That is, here real part is 1 by 2 log of x square plus y square, and the imaginary part v is equal to tan inverse of y by x. Now you have to find dou u by dou x. So 1 by 2 is constant here. Log x derivative is 1 by x. So in the place of x we have x square plus y square. That is 1 by 2 into 1 by x square plus y square into x square plus y square derivative is 2x. So 1 by 2 cancel, then we can get the value is x by x square plus y square, same as dou u by dou y by x square plus y square. So dou v by dou x, tan inverse x derivative is 1 by 1 plus x square. In the place of x square we have y by x whole square, then simplify it, we get y by x square plus y square. Dou v by dou y is x by x square plus y square. We need to check both, and that is we can go CR equations. CR equations are dou u by dou x is equal to dou v by dou y, and dou u by dou x is equal to minus dou v by dou x. So we can write w equal to log z. CR equations holds good for x square plus y square is not equal to 0. Dou u by dou x is equal to dou v by dou y. Both are equal. You have to see this, x by x square plus y square and x by x square plus y square. Dou u by dou y equal to minus y by x square plus y square. So we can get here, because of y we get minus. Clearly you can see this dou v by dou x. So 1 by 1 plus x square into y by x derivative is, here y is constant and 1 by x derivative is minus 1 by x square. So that's why we can get the here negative sign. Here also same procedure you can follow it, but here with respect to y, no, so the y by x derivative is 1 by x. So simply you can find the derivatives, and CR equations are equal. So that's why it is analytic. Then we have to find dw by dz. So dw by dz is equal to dou u by dou x plus I dou v by dou y. We can substitute the values already. We find x by x square plus y square minus, because of dou v by dou x value is minus I y by x square plus y square. So dw by dz is equal to x minus I y by x square plus y square. So we can write z bar by z bar into z. Because of r is equal to z bar into z, we can write it z bar cancel 1 by z. Otherwise we can find dw by dz is equal to 1 by z, because of w equal to log z derivative is 1 by z. Simply we can write it. Otherwise you can write by using dou u by dou x and dou v by dou x also. So thus every point other than origin w equal to log z is differentiable, and the function log z is analytic everywhere except at z is equal to 0, because of here CR equations are satisfied and differentiable also. Function is also differentiable, but at z is equal to 0 it is a non-finite, means infinite value 1 by 0. So that's why except at z is equal to 0. Z is equal to 0 means x plus iy equal to 0. X value 0, y value 0 means it is called origin. Except at origin the given function w equal to log z is analytic. That's all for today.